I'm going to calculate the magnetic field produced by two long wires. In the figure is an end-on view of two long straight wires shown here and here. Wire 1 lies on the x-axis at a position x equal minus d. Wire 2 lies at a position of x equal plus d. The current in wire 1 flows out of the page and the current in wire 2 flows into the page. We're going to calculate the magnetic field vector at the point P1, P2, and P3, all of which lie on the x-axis, with P1 at a position of x equal minus 3d, P2 equals x equals 0, and P3 at a position of x equal plus 2d. In part B, we're going to find an expression for B at any point on the x-axis to the right of the second wire, so anywhere over here. So the equation we'll need for this is equation 28.9, which gives us the magnitude of the magnetic field of a long straight conductor as a function of the distance from that conductor. And of course we're going to use the superposition principle. So the total magnetic field at the point P1, for instance, is the vector sum of the magnetic field due to wire 1 plus the magnetic field due to wire 2. We're going to use the fact, of course, that the magnetic field by the right-hand rule around wire 1 flows in this fashion. So it flows in a counterclockwise direction, and of course for wire 2 it's in the opposite direction. This means that the magnetic field due to wire 1 at any point to the left of wire 1 will be downward. Likewise, the magnetic field at any point to the right of wire 2 will be downward. And the opposite is true on the other side of these wires. So now we're ready to begin. So the first thing we've got to do is get the magnitude of the magnetic fields at the point P1. And here are the two magnitudes, where I replace R in the first case by 3d minus d, which is 2d, and R for the second case, for the second wire, is going to be 4d. And here's the two magnitudes. The two magnetic fields, however, are in opposite directions. So the magnetic field due to wire 1, which is the bigger magnetic field, is down, and the other wire has a magnetic field up. And of course, up and down refers to the plus and minus k hat direction, or j hat direction rather. So here's the final expression for that magnetic field. At the origin, the two magnetic fields have the same magnitude, and in fact, the sense of flow of magnetic field is the same at the origin. They both point straight up, and so the total magnetic field is equal to mu naught I over pi d at the origin, pointing in the positive j hat direction. So the two fields simply add there. At point P3, the magnetic field due to wire 1 points up, and the magnetic field due to wire 2 points down. And here are the two magnitudes, again, taking into account the distance of P3 from wire 1 and wire 2. And here's the total magnetic field at that point. So now I want to get the magnetic field at any point to the right of wire 2. Let's take this one, which is at a position x. Then again, the magnitude of B1 is equal to mu naught I over 2 pi x plus d. I got to take the distance from here to the origin plus d. And likewise, the distance, the magnitude of the magnetic field due to wire 2 is mu naught I over 2 pi x minus d. And the field of wire 2 points down, the field of wire 1 points up. I can get a common denominator at this point, and here's my final expression for the total field to the right of wire 2.